Okay, so when we finished in the last class, we looked at two control schemes, the joint space control scheme followed by, well, in this we were doing inverse kinematics, and then once we got the desired joint command, we were simply doing a single axis joint control. And we said there are two sub problems, one is doing the inverse kinematics and then closing this loop. Now, then we looked at the operational space control scheme, in which this inverse kinematics is now embedded in the loop. So, you have to compute it and then compute the torque real time, and I pointed out that there is no potential advantage unless you can actually measure the position or the force in the operational space, in the coordinate. So, if you are inferring the position of the end effector through the joint by doing forward kinematics, then there is no advantage to using this method. If you are measuring the force at the end by measuring the joint torques, then there is no advantage to using this method. So, with this come to the new material. So, like I pointed out earlier, controls essentially deals with using elements of dissimilar power ratios, okay, the transducer and the actuators. And so, the whole issue with there is trying to figure out what arrangement, what combination, what feedbacks will give you a structure which is more easily controllable. Okay. So, if you take very simple, I mean very complicated example, when you say take cricket, right, you want to come in and bowl. So, what do you do if you have your leg in the right position, shoulder in the right position, wrist in the right position, then you can control where you are going to deliver the ball. Now, if you do not have them in the right position to start with, then it is much more difficult to do it in the last minute, and then the ball gets sprayed. So, that is why when bowler is not been able to control it, his coaches work with it and get the mechanics and the structure right. Now, it is the same person with the same perception abilities who is working. So, the whole idea is how do you put your structure together, how do you create your loops and internal controls so that it becomes manageable. So, we will assume we start from this model which we are quite familiar with by now, and we know that this has been derived from the Euler-Lagrange form, but we can find the B matrix, C matrix, whatever we want, FV, we can find it from the, well, FV is known from some other parameters, G is known, but we can find the C matrix also by using the Euler-Lagrange method, by using the Newton-Euler method. We will simply set Q dots to 0, and then we will take one Q at a time, and we will find C column by column by computing the corresponding torque. So, irrespective of which method we go by, we can usually get an equation down in this form, and this is the form from where electrical engineers start their controls problem given this. So, we will also start from here and see what we can manage, and this model is reasonable, and we have dropped the H of Q term which is there, which you can easily incorporate. We have assumed that there is no static friction, primarily because it is very difficult to model accurately. Viscous friction is still okay, it is a stable parameter, but static friction is very difficult to model accurately because of basically what is called the stick effect. So, you are static and then you start moving, there is a sudden drop in the friction. This is very difficult to model mathematically and creates problem with the dynamical systems. So, currently we have just dropped it, saying that we will take care of it as a disturbance, and you always try to make sure that these values are not very large because they are unpredictable. So, then from this you determine the components of the generalized forces. If it is a revolute joint, determine the torques. If it is a prismatic joint, you determine the force. You determine what is the desired joint trajectory vector QD as closely as possible, corresponding to some motion. Now, there are two terms, there is this joint thing and then there is a vector of actuated displacement. So, the motor is connected to the joint through a reduction drive. So, the rates are not the same. We get the joint rates and the joint values by doing inverse kinematics on the manipulator structure, and then there is a motor, and that is connected through either gears or something, gears, belts, timing belts, to the actual physical mechanical to the link joints. We assume the transmissions are rigid. So, if you are using a belt, immediately that goes for a toss. If the loads are high, even gears are not rigid, the teeth actually deform. Okay, so, there is a problem there. We assume there is no backlash, and you know that is a big call. You do get backlash free gears, but they are expensive and they are large. Okay, so, if you are making a missile, you can put it in there, no price asked, but for making cars, you can't afford the price. Basically, if you want motors to make a welding robot, then you can't afford the price. And we understand that there is this Kr, it is this transmission ratio, and Krq is equal to Qm. Okay. And this Kr is a diagonal matrix, because the motion of the reduction, the motion of one link does not affect the motion of the other one as far as the reduction ratio is concerned. So, these are basic assumptions which are there, and typically these diagonal elements are order of 50 or so. Okay, the reduction, step reductions are order of 50. It is not 2, 3 reductions that you are looking at, okay, which you see in other places. So, large reductions. So, if you have motor as an actuator, now if you go back here, I am saying that the displacement Kr times Q is equal to Qm. So, torque will have a inverse relationship, right. If through the transmission ratio you have increased the velocity and the angle of motion, then the torque will reduce because of the transmission ratio. So, that appears as a, well, in scalars you divide, in here you will have a matrix, you will have an inverse operation. The next thing is that you know for a motor, if there is a current A in the armature, then that multiplied by a torque constant will give you the torque at the motor, and that can be brought down into the torque at the joint through this Kr term. And then you have the, if you are applying a voltage A at the actuator end, then that voltage A is equal to the coil armature resistance times the current in the coil plus a term which is the back EMF term. You remember that from the motor control, that the faster and faster the motor runs, it acts as a generator also, and it generates a voltage which is exactly, which opposes the applied voltage, and in steady state we are going to cancel things out if you are free running and there is no torque acting in the system. And this kV and kT are actually related, that you can find out. And finally, you assume that there is a control voltage which is applied, which is amplified to form the, by the gain of the amplifier, and this forms the voltage applied across the field of the motor. Okay. And then so we have a list of all the parameters which is given here. Okay. So, this Kr, and then the warning that if the reduction ratio is increasing the speed, then it will reduce the torque. So, the inverse relationship. So, armature currents, armature voltages, armature resistance. So, thing missing here is inductance, which I have just chosen to ignore, because in a decently made motor for which you have dished out 5,000 rupees, armature resistance, inductance is actually very small. You make it out of nice plates which are insulated from each other, so you do not have eddy current losses. So, it is not a big deal. So, remember we started from this equation. So, this is written as tau. So, it is the same equation which is here. Now, I am introducing, so these two terms, there are no, so these are the same terms, there is no change here. I am introducing this term Fq dot. Okay. And what is F? F is Fv plus this term. So, if I write Fq dot, I am writing Fv times Q dot, which is here, plus I am introducing an additional term on the left hand side. So, I must subtract this term on the right hand side. So, this term into q dot is subtracted, so it becomes tau minus that term, and the u is defined as this portion here. So, then if you subtract these two, so you have finally land up with this expression. Okay. So, we write tau as the sum of the control plus feedback terms by going back into those equations which you had here, substituting for tau from here. So, you will end up as with this. So, this is the additional equation which I generate. By using the motor equations, I can write expression for tau in terms of Vc, right, that you have done in the controls course. Use that, so then you get this. Then you have u, which is a function of Vc again. So, this combination finally gives you the equation in this form, and you just move tau over to one side and you move this term over. So, Kr Kt Ra minus 1 comes outside and you get Gv times Vc, which is this, minus Kv Kr q dot. This is a little bit of algebra done on the matrices. And then if you look at this, so the overall system is voltage control. I just have Vc here, and we just assume that there are a couple of assumptions that this Kr terms, like I already mentioned, are significantly greater than 1. So, 10, 20, 10 is on the borderline, so 20, 50 is pretty good. Armature resistances are small, right, as typically what you get in high efficiency servo motors. Torque tau required for the execution design motions are not too large. Now, the smaller RA is, its inverse becomes larger and larger, right. Similarly, these terms. So, now if this term becomes very large and your tau is bounded, then tau divided by this term becomes smaller and smaller. So, essentially this term will tend to go to 0 or relatively compared to this term. So, when you have this situation, so if RA is small, its inverse is very large, then for small values of tau, see if there are two terms, suppose I give you an equation which is A is equal to B times C, right, and this A tends to 0 and this A tends to, well, let us say infinity, a large number or a large number. So, then this, to satisfy this equation, then this C has to, this has to also tend to 0, right, because if this is finite, then this into a very large number cannot ever become equal to 0. So, if this becomes, this tends to 0, okay, so actually this is the wrong notation, I should use A tends to 0 is equal to B, which is tending to a large number, into C, then C perforce has to also tend to 0, right. So, if you use this, then this term in the bracket Gv into Vc minus Kv Kr q dot, that whole term in the bracket will tend to 0. So, you get this term, which is very nice, which says that the joint rate is proportional to the control voltage. So, essentially you say, okay, isn't something funny happened here, because I started by looking at equation of a robot, of a manipulator, in which you had all these nice complicated terms which I spent 1 month deriving or 3 weeks deriving, doing dynamics, back forth, Euler, Lagrange, Newton, Euler, and all of it I am throwing out of the roof and saying, okay, because you look at these terms, this is amplifier voltage. What is Kv? It is a back EMF constant, which is a motor property. What is Kr? It is a transmission ratio between the motor and the joint. So, all your manipulator, kinematics, inertia, everything is thrown out of the roof, and you land up with pretty simple a mechanical transmission ratio and the motor properties which are there, and amplifier gain, which relate the angular rate at the joint to the applied voltage. So, this is brilliant, and luckily somebody has done it for you. So, we do not have to worry about it. So, this is just to remind you of this equation when we use it. So, this essentially this controller, so basically you just move GV over to this side and you get VC is GV inverse KV KR Q dot, and I am writing approximately because we took this equation and we modified to just this equation equal to 0. So, this tau being divided by this is approximately 0, it is never exactly 0. So, this is independent of the state of the manipulator, you do not care whether manipulate in this posture or in this posture or in this posture. The smaller the joint velocity and the acceleration, the smaller the required torque, we know that. So, the assumption becomes more and more valid, and it is robust because robust with respect to parameter variation of the manipulator model. So, if your link has your link joint has a little friction here, a little friction there, it is slightly teda, so that you do not know the moment of inertia correctly, it does not matter, it will still work. And if you have large gear reduction ratios, then it becomes better. Okay. So, essentially your reference structure becomes this. So, your control voltage has to be GV inverse KV KR Q dot, so which is available here, and this becomes the reference structure. So, this is the model for the system, the rest does not matter. So, life is very easy once you do something like this, so you get a sense of it. So, velocity at the ith joint depends only on the ith control voltage, since this matrix is diagonal. Okay. Amplifier gains, you do not want one amplifier gain to be effective, another one. Electrical engineers can do a fantastic job of that, decoupling each amplifier. Okay. There is no problem, and there is no reason to expect that the speed at one motor will affect the back EMF in another motor. Okay, that amount of isolation is there, so we are not worried about it. Reduction ratio, I do not think the reduction ratio at if there is a motor which is turning and moving a joint at a certain rate, it will affect the reduction ratio in some other joint. I mean, mechanical engineers do a good job of ensuring that that does not happen. It could happen if when you rotate this starts vibrating, then you will have a problem on that end, but you can design things so that they do not vibrate. So, all of this is presumed that that each guy is doing his job properly. So, if each guy is doing the electrical engineer is doing his job properly, mechanical engineer is doing his job properly, then you can forget about the robot in the middle. Okay, so you can just control each joint independently of the other. So, we could have stopped this course roughly at inverse kinematics level. We need not have done dynamics, except we would have been worried that what will happen if all these couplings are there. Currently I am saying you do not need to worry about it as long as your torques are small, I mean relatively small compared to what? Compared to some things, right. So, we will see what they are. So, if you are looking at performance, now when you say performance, you have to understand what are you evaluating for performance. So, if you are just trying to track accuracy of joint variables with respect to desired trajectories, if you have higher gear reduction ratios and less demanding values of speeds and acceleration, then you will get good performance from this, if you have these conditions. And certainly, if you have a direct drive actuation, Kr becomes essentially equal to 1, this is not a valid approximation. So, then you have a problem. So, we can't ignore that. Sometimes we want things to move fast, right, and we make things very light. So, moment you make things very light, there is compliance, right, and you still want to control the manipulator so that it works, right. So, for example, these three guys sitting back there are designing a manipulator which has flexible links. So, there is compliance. Now, if you want to control that manipulator, you are going to have to mess around a little bit more. Now, how much more is what we need to see next. That is still doable. Now, we can do inverse dynamics anyway, right, and compute joint torques, need to track specified motion in terms of Q double dot T, Q dot T and QT. If you know these terms, we can always find out the joint torques. The only thing is, to do this, I must know the manipulator dynamic model quite accurately. So, that 3 weeks you spend doing Euler-Lagrange, Newton-Euler comes in useful. Okay. So, it comes in useful when you are moving things very rapidly and things are compliant. And now, this one needs a centralized control structure because there are cross links. You cannot do one joint at a time and just let go. So, you need that full information as to state of the manipulator coming in, and you need a CPU where you are going to do some computations, do the dynamics, and then give output out to individual motors sitting on the joints. So, it has to be a centralized control structure, and it is better in this case to use what are called torque control motors. So, what do you do in torque control motors is that you use a voltage controlled current source. Did you do VCCS? Voltage control voltage source, voltage control current source, current control voltage source. You can reconfigure an op amp to do all these things. No? You have done course in electrical engineering, right? Yes? Forgotten everything. So, it is not very difficult to design a electrical circuit. I shouldn't say it is not very difficult, it is still difficult to design electrical circuit because 99% of the population, maybe 99.9% of the population cannot do it, but most electrical engineers are able to do it. You can design a circuit where if you give voltage at the input, it will produce a constant current. Constant voltage produces a constant current. Okay. So, for example, a transformer will not do it ever, right. If you give AC voltage, it will produce a constant voltage at the other end, and so the current will depend on how much is your resistance at the output end. Similarly, but this is a special circuit where you produce a current which is proportional to the voltage. It is available. So, for mechanical engineers, you go and buy a module from one of these companies which will give you the necessary things. So, if you do not do that, then it turns out that the tau becomes equal to the u, and this is equal to kr kt gi vc. Okay. And when you do this, let us just compare with this equation. We see that this Ra term is gone and the kV term is gone. Okay. So, what has happened is I am less dependent on the motor parameters now, but all the manipulator parameters, the link lengths, the geometry, the mass, moment of inertia, everything is all of them enter the picture. So, given these terms q, q dot that I want out of it, I have got to calculate what is the desired tau, and then I have got to multiply it by kr kt gi inverse to get estimate what the Vc is, and then feed it, and then everything will work in the system. So, this is the basic change. We use decentralized structure, the individual joint control approach when we want robustness. So, we really do not care whether you have a little manufacturing error in the manipulator and things like that. It should work reasonably well, and it is essentially a feedback control system. You need a centralized, if you do centralized structure, then you need to compute the inverse dynamics, and this is a feed forward control system. We call this feed forward because you are computing ahead of time what the torques are going to be, and then you are adding to it, to the system. So, it is actually fed forward, even before you are using it, you are calculating it. It is called a feed forward system. The catch is that the dynamic model, though we derived and appeared very complex, it is already idealized. I mean, we affected, we are not very comfortable, at least I dropped the Coulomb friction term, backlash, dimensional tolerance, compliance, all of them we have dropped. So, even this messy thing that I did with the Christoffel symbol, no Christoffel symbols, the Euler-Lagrange, I mean there is a level of inaccuracy about it which we have to keep at the back of our mind. So, this cannot be, the feed forward action cannot be ever be fully accurate. So, you still have to use the error between the desired and the actual trajectory even for the feed forward control. So, there is no open loop that I will compute everything out of this. So, for the centralized control, you just calculate the driving torque from a reduced manipulator dynamic model. As we saw, we dropped several terms and we just calculated it, and the drive is essentially a torque control generator. So, the motor generates torques given a voltage, that is the basic structure, and you do not use the full manipulator dynamic model, you use a reduced version which will basically take care of the cross couplings and things like that, the inertia changes. Some of the terms we are saying, okay, we will take care of it through feedback. We do not need a fully idealized model for this also, it works reasonably well. So, now given this basic approach, we have to look into more details and actually come out with the full structure for us to be able to use it properly. So, we take n independent systems, assuming that they are n joints. So, you have to control each axis as a single input single output system, and so in this case the reality is that there is actually coupling which is there between the system. So, we assume that they are disturbances. So, if we assume that disturbances, so there is a, what we have to do, well, we will look at the structure. So, it is more convenient to refer everything back to the motor rotation. Okay. So, if you refer everything back to the motor rotation, then I had B of Q. So, B of Q I want in terms of B of Q of the motor. So, I have to multiply by KR inverse. This is originally it was in terms of Q of the joint, I want in terms of QM double dot. So, I have to multiply by KR inverse. So, I just keep on doing this over and over again everywhere. So, I get this term which is sticking out here. So, you get into this form. Now, this B matrix, now this is a typical example, we derived it for the small manipulator. This is typical structure. So, this has lots of constant terms and some terms which are dependent on positions, theta 2 term here and so on and so forth. So, what you do then, you take the B matrix and split it into two parts. One part which is largely constant, and you take only the diagonal elements. Do not take the off diagonal element, because the off diagonal elements are the coupling terms, and write the remaining as this plus delta BQ. So, for example, for B11 you take this term, this term, this term, this term, this, you leave this out, take IM2 and this. So, in delta B11 you would have only one term which is ML2 multiplied by 2A1L2 cosine of theta 2, okay, if you can read that, you can look it up. So, the only just term, that term will be then B11, however, all of B12 will become delta B12, okay. So, that is the basic structure. So, this I have not done anything, I have just kind of split a matrix into two parts. So, having done that, so we separate this essentially into a diagonal B and a varying delta B. Okay, this is the varying and coupling delta B terms. So, what you then do is you just rewrite this original equation which we had here into this form, where I am now keeping all the constant terms out here, right, and Fm Qm dot plus D, and then this D contains all the configuration dependent terms, okay, and Fm is the viscous torque about the motor axis. So, I have just separated these two. So, obviously what I am trying to do is I am trying to find out two systems, one which is invariant and one which is variant. So, I then get two systems, one here, another one here, okay. Now, this lower block that you have, this has Tm as the input, and the output of this is Qm double dot, Qm dot and Qm. Well, output is actually Qm double dot, but you can obviously integrate it and you can find Qm and you can find Qm dot. So, basically input is torque, output is motion. Now, this block takes in Qm double dot, Q dot and Qm dot, Qm as the input, and outputs that term D which I derived here, which contains all the variable terms. So, this is just a graphical representation of the mathematics which I did. Now, this part is a linear and decoupled invariant system. This part is non-linear, coupled and variable, okay. So, this part is a mess, this part is something that you already know how to handle, okay. So, linear decoupled invariant system, you can use your automatic controls course and you can design a controller for it. You can do everything with it, right? You can do root locus, you can do pole placement, you can do, and you know how to get performance out of it, how to get it to reject disturbance, and all of this becomes essentially disturbance into the system. So, now all we have to do is we have to design feedback here so that this disturbance gets rejected. Now, obviously, if a disturbance is very large, then systems do not work, then it has to be modeled. So, we assume that the disturbance is small, but it is there, which is fine. So, if you have been wondering why does the disturbance come in, okay, disturbance is a little bit different from noise. Noise can be, so externally they can come noise. If you are plugging it into this power supply here in the room now, because the AC is running, it is a high power device. If you look at the signal, you will not get pure thing, you will find spikes all over the place. That is noise, yes. But disturbance in control comes from lots of unmodeled stuff. In this case, we are explicitly showing what is the nature of the disturbance when you are running a manipulator. So, each joint, what we want to do is we want to work, each joint is controlled independently of the other, that is very nice, and we just must make sure if the joint controller must have high disturbance reduction and trajectory tracking capabilities. So, you can design for that, and the controller is driven by the error between the desired and the actual output, that is pretty there, and the control torque at actuator I depends only on the error at output I, nothing else. You do not need to look elsewhere, and we know how to design controllers for this kind of invariant stuff. So, how do you do that? You estimate this, if you look at this structure, this is essentially the motor, okay, KT RA 1 upon IM, and this IM, I mean for the ith motor it is essentially BII divided by KRI, which is not a big deal, you can always compute it, and you can drop it, since this is a single actuator, nothing else is involved, you can drop the indexes which has been dropped here. So, this is the motor. This is just a way of representing that, okay, I am getting out of this, I am getting acceleration. If you do 1 by s, integrate, you get velocity, and then you integrate it, then you get theta m. And there is an internal loop. So, the motor velocity through kV is fed back internally. So, this is the motor structure which is there, and this is all that there is there to it, and inside this we have incorporated this BII term. So, the manipulator is gone, you just have the motor with a modified inertia parameter, the rest of the manipulator is gone from this structure, and this is something that you already know now. After that is that you have feedbacks proportional, velocity and integral, okay. So, you can have these feedbacks and correspond to each one of them. This is what is called a cascaded filter design. So, you can either do a cascade or you can bring them in and you can club you can do a reduction and you can make this all of this into a single controller. This you should have done in the controls course. So, I will not get into it, you just go back, look up your controls, okay. So, you should be able to design this for performance of any kind that you want, and so this dr A upon KT is that you take the component of the vector d and you, so that is torque, right. Now, when you are running the circuit, I want it to become a voltage, so you multiply it by RA and divide by KT. Now, what is KT? It is the torque for a given current, and RA is current for a given voltage, right, a resistance value. So, this is the factor by which you convert the torque into a voltage. Now, these are important numbers for you to actually implement this. You can put it in a loop, but knowing this is important, that how does your torque get converted into a voltage. Yes, you can measure the torque. Suppose you are measuring the torque from any system, output you will get is a voltage, but unless it is the voltage which is modified by RA upon KT, then you will not get the same circuit back. So, this is an important parameter. The second thing is that the other thing is you need integral action on the controller, okay, to cancel the effect of gravitational component in the output at steady state. So suppose you want to go to a constant theta m, if you have integral effect, it will slowly cancel out the gravity component, because that's not been modeled at all in the system. And so when you want to track it, now question is, this system will drive it until this error and this error and this error goes to 0, right? Now this error, now if I have theta m value here, right, suppose you take this, at this point the value is theta m into KTP. So this input voltage that you must give to this has to be this theta desired multiplied by KTP. Okay, so that must be the voltage which is coming into this system for it to work. So this is the reference input which you give for it to go to a particular position theta. So these are again design parameters. So this you can all pretty much get out of the system, because you are designing this, you know what this should be, you know what is desired, so multiply by KTP and feed it into the system. Usually most of this is done digitally in the microprocessor. You do not actually have these physical blocks anymore. You have some current amplifiers at the end of it, which is a separate issue. Okay. So this figure makes some sense, reminds you of something which you have done in the previous semester or previous year or something. Previous year. Yes, no? No? You have done a course in controls, right? Didn't like it. So next thing is you look at the feed forward compensation, and another nice block. So here is the manipulator, and we have the noise part coming in here, we have the desired motions here. Now I feed this back and I compare with the actual position received. Okay. But in addition, what am I doing? I am computing what is the torque required, and that is based on theta md, theta dot md and theta double dot md. So this into B. I am summing all the torques up and then feeding it forward, and this is a saturation thing, because there is you cannot demand infinite amount of current or a torque from a motor at no time. So you can demand a fairly high velocity for a motor because it will keep on spinning up till a certain limit, but torques are very limited in terms of saturation. So you saturate this, and then that creates a little bit more of a problem, but there is saturation. There are various saturations which are there. So you take care of that in the model, and this is a simpler block than the other one. The only thing is that to calculate, you have to estimate theta dot md and theta double dot md, what are the desired values, and then it is fed forward into the system. So this is the additional problem which you have to take care of it. Now there is a interesting practical implication of both these systems. For this feedback to work, I need to know what the acceleration is, I need to know what the velocity is, I need to know what the position is. I have a joint, I have a motor there, and yes, I can put an encoder, I can put a tachometer. And how do you measure rotary acceleration? Any idea? Never asked yourself. You know what's an encoder? Yes, no? Yes, no? Yes? What is it?
Encoder basically measures the angle which is traversal angle by rotating with the surface, rotating with the wheel.
Okay.
Which is what exactly has been traversed.
And what's a tachometer?
Measures the RPM.
Measures the RPM. Where did you learn this? General knowledge, or is it some course? Course? General knowledge. Did you ever ask yourself, how do I measure angular acceleration? No? No, terrible. You ask yourself questions, no. What is the area of a circle? Simple question. Huh? That you know, right? Yes, no? What? Come on, commit yourself. You must know this. Area of a circle? Pi r square. Yeah. Area of ellipse? Pi ab. Perimeter of a circle? 2 pi r. Perimeter of ellipse? No? Pi a plus b? No. Many interesting things like this. Huh? If I give you a line, can you bisect it into two parts? Yes, confidently, right? If I give you an angle, can you bisect it into two parts? Confidently. Line, can you trisect it? Confidently, right? Yes, no? Come on. You draw a line at an angle, divide it, take a compass, make three parts, join the ends and then draw parallel lines. Right? You can confidently trisect it. Given an angle, can you trisect it? No?
Quadratic operation.
Quadratic operation? What is that?
All the compass and scale are quadratic. So you cannot trisect it. It comes out to be
Becomes what?
I mean, it cannot be trisect.
It cannot be. So you cannot trisect an angle.
Using this compass.
It's a problem, no? So how do you ever make 20 degrees on the compass, on the protractor? So 60 is fine, you can bisect it, you can make 30, you can make 15, right? So how do you make 20 degrees on a protractor? So these are interesting questions, you must ask yourself before you get out. So they are all related to robotics actually. So that's why I am asking this question. But anyway, so no, they are not related, there is general knowledge. Now similarly, there are things which measure angular accelerations. Now question is, if I now put in a device to measure angular acceleration, you can find out homework. Okay. So I put that, then I put in a tachometer, I put in a encoder, and I have my motor, so my joint becomes this big. It's not desirable, right? So what do? You put an encoder, and then to find velocity, what do? You differentiate it, right? So digitally you will take finite differences, right? And then you take another difference and you get acceleration. What is the problem with this method? Come on, differentiation is a noisy process. Somebody must have told you. No? Yes, somebody told you? Who? Huh?
Heard something about like
You just heard something about it. What about you? Where did you hear that? In controls. In controls course, and you guys didn't hear it. You guys are on the same course, right? No, not in the same course. No, but what about you? You're a EE person. You're not EE. You're mech. Same course, right? No, not the same course. Oh, acha, different years. Same teacher. Come on. Anyway, so this is a noisy process, right? So essentially, so the signal becomes noisy. Now the way you stop it from being noisy is that you increase a band and you do a low pass filter. Now you do that, then you introduce a delay. You introduce a delay, then it becomes unstable. System becomes unstable. So it's a chicken and egg problem. So there's a huge, so there's an issue here. Now if you are doing this feed forward compensation, the only term which is actually fed back is the position. So it's very nice. So you don't have noise, and you can straight away, so you don't have noise, you don't have lag. So that's very nice. The issue then you might ask me is that yes, but I need all these values, I need to calculate these. but these are desired values. So, moment you give me a trajectory, I can sit offline and I can calculate all the derivatives, and if I am doing a spline fit, I know that locally I have a cubic fit, so finding accelerations and velocities is something that I have been doing since class 12. Okay, so we can do that. So that is not a problem. So this is something which is really good, and that is why you want to try this decentralized feed forward compensation, unless you have no problems. You can put in a what is called magneto-hydrodynamic acceleration pickup, and you can put in a tachometer and you can put in a encoder. You don't mind, just put it in, pack it in, and then you run slowly. So then you can use the other method, but if you are whipping around fast, quick, and you don't have space, then you can pretty much use these devices. Okay. All right, so I'll stop here.